Let's talk about how to measure temperature. For this we use a device called a thermometer, and the thermometer measures the temperature of a system based on a physical property that varies in a very well defined way with temperature. So we call that parameter thermometric parameter. The thermometric parameter can be um, for example, volume of a liquid, volume of a liquid. It can be dimensions of a solid. It can be another physical property, pressure of a gas under constant volume, volume of a gas under constant pressure. Electrical resistance varies with temperature, so we can use that. Sometimes the color of an object varies with temperature, etc. So there are many physical properties we can use as a thermometric parameter that varies with temperature in a nice way. So here's one example. This is a mercury thermometer. And what is the thermometric parameter in this case? Well, the mercury thermometer, if you look at it, it's a column that is filled with mercury. And because the cross-sectional area of this column is constant, there is a very small column here. And if you find the cross-sectional area of this region, so that's a very small region here, cross-sectional area that's a constant. Therefore, we find that it's the column of the mercury that varies with temperature. So it's the volume as a function of temperature we can use, but because the area is a constant, that implies it's the height of the mercury. So you can see here we can get a reading of the temperature by looking at the level at which the mercury reaches, the mercury column reaches here. For example, here it is 20 degrees Celsius. Here it is 30 degrees Celsius. So what do we mean by degrees Celsius? We have to calibrate every thermometer with a system whose temperature is very well known as a reference system. So the Celsius scale that we use in the mercury thermometer is calibrated against icy water and boiling water. And when we put the mercury thermometer into icy water, we label the temperature to be 0 degrees Celsius in icy water. This is the melting point of ice or freezing point of water. And we label the temperature 100 degrees Celsius in boiling water. So once we have this labeling, so we have created a column with labels on it, and here we said this here is 0 degrees Celsius and here is 100 degrees Celsius, because the temperature, the height of the column changes linearly with temperature. Basically we can label all the other intermediate temperature readings using a linear scale. So we can put markings for right in the middle, I would say 50 degrees Celsius. Here I would say 75. Here I would say 25, etc. Now, if you have different thermometers that you can use to measure the temperature of a system, they will agree exactly on the calibration points. So this is an important remark. Different thermometers agree precisely on the calibration points. So if I have to read an intermediate temperature, let's say 25 degrees Celsius or so, using different thermometers, due to slight differences in the thermal expansion coefficients, due to slight nonlinear dependence on temperature of the physical property that this thermometer uses, the thermometric parameter, we can have slightly different intermediate temperature readings. But we are guaranteed to get precisely the same reading on the calibration points because all these thermometers were calibrated against the same calibration points. Now I want to look at another thermometer. It's the constant volume gas thermometer. Constant volume gas thermometer. And how does this thermometer work? You have a gas inside the flask and the volume is kept constant by lowering reservoir B to keep the mercury level in column A constant. So this level we have on side A, this level is kept constant, so that is not changing. So I have a constant volume gas, and when I put this gas inside a liquid, a bath or environment to be measured, I see that the mercury in the column will change its height depending on the temperature of this gas. And how does this work? The pressure outside the mercury is, this is open to air, so I have a pressure of P0, that's atmospheric pressure, and the mercury will rise until the levels here, these two levels, will correspond to the same pressure. So the pressure of the gas in the constant volume, pressure of the gas, must be equal to the pressure, outside pressure P0, plus the weight of the mercury inside this column. So it will be its density of the mercury, GH, which depends on temperature. So the density is mass per volume, so it's H will get rid of the volume, it will give you an area, so it's mg per area, that's the additional pressure due to mercury. So you have a pressure differential here between these 2 points. The delta P is the weight of the mercury, m mercury G divided by cross-sectional area, perpendicular cross-sectional area. And where is that perpendicular cross-sectional area? It is this area. This is area A. So, and remember that is not changing in this column. So I have rho GH giving me the additional pressure due to mercury. Now, since the pressure of the gas will depend on temperature, it will be reflected as the change in the column height of mercury. And why does the pressure of the gas change with temperature? We have ideal gas law, which says that pressure of a gas times its volume is equal to number of moles of the gas, universal gas constant, times temperature. If V is constant, the number of moles in the gas is constant, R is the universal constant, I find that the pressure of the gas under constant volume is proportional to temperature. So that's how it works. And this one is also calibrated at icy water. In icy water, so we have 0 degrees Celsius, and in boiling water we have 100 degrees Celsius. So if you look at the calibration of this thermometer, you will see that these two are your calibration points. Here is one calibration point, here is the other calibration point, and then the rest is a linear dependence. Pressure changes with temperature linearly. Now what is interesting here is that if I repeat this experiment for different gases have different pressures in the constant volume gas thermometer. I see that whenever I do this experiment with these two calibration points, so here are the calibration points, the PT relationship is always linear, but then I find that they will always extrapolate to a single point on the temperature scale. So for all different constant volume gas thermometers, I see that the zero pressure reading corresponds to a temperature of minus 273.15 degrees Celsius. Alright, so I observe a zero pressure at a temperature of minus 273.15 degrees Celsius. Because this is a universal reading for all constant volume gas thermometers, we call this temperature absolute zero temperature. So this is my absolute zero temperature. It's the temperature at which a constant volume gas, has zero pressure. In order to create a new temperature scale out of this point as one calibration point, I have to choose one more calibration point. So this is the first calibration point. Now if I choose another calibration point, which is another very reproducible point, temperature is equal to 0.01 degrees C at 4.58 millimeter mercury pressure for triple point of water. What is triple point of water? Gas, liquid and solid coexist. So this is another reproducible point. It's the second calibration point, and this gives me the absolute temperature scale, and I use the unit Kelvin in order to measure temperatures in the scale. And for Kelvin, I don't use degrees, it is just Kelvin. So I label this point. The first calibration point is labeled T is equal to 0 Kelvin. The second calibration point is labeled T is equal to 273.16 Kelvin. Therefore, I can label any other intermediate temperature by using the linear scale, linear dependence on temperature. So Kelvin is the SI unit of temperature. SI unit of temperature. Now, there is one more scale that is commonly used in United States and in UK. That's called the Fahrenheit scale. So I would like to just explain how you can convert between these three different scales. So let's summarize here: the Celsius scale, the Fahrenheit scale, which I'm going to introduce in a minute, and Kelvin scale, absolute temperature scale. Okay, so all we have to do is to look at two calibration points. Icy point of water, melting point of ice is 0 degrees Celsius. In absolute temperature scale, this is 273.15 Kelvin. In Fahrenheit scale, this is labeled 32 degrees Fahrenheit. And 100 degrees Celsius, the boiling point of water, is 373.15 Kelvin in the Kelvin scale. In Fahrenheit scale, this is labeled 212 Fahrenheit. So I can see that if I have a change in the Celsius scale, first of all, how do I go from Kelvin scale to Celsius scale? Temperature in Kelvin scale minus 273.15 degrees Celsius is temperature in Celsius scale. For example, if I have 0 Kelvin, that corresponds to minus 273.15 degrees Celsius. Now, if I look at a change in temperature in the Celsius scale, delta Tc in Celsius scale, you can see that it's going to be the same change in Kelvin scale. All right. However, I see that if I have a delta Tc or delta T of 100 or delta T of 100, this corresponds to a delta T in the Fahrenheit scale of 212 minus 32, 180 degrees Fahrenheit. So basically, a 100 degrees C temperature change in Celsius scale or 100 Kelvin temperature change in the Kelvin scale is equal to 1 over 18 times 10 delta T in Fahrenheit scale, or I can rewrite this: a change in Celsius scale is the same change in Kelvin scale, is 5 over 9 times the change in the Fahrenheit scale. So this comes from this information about the calibration points. So if you have a change in Celsius scale, it's the same change in Kelvin scale, but it's 5 over 9 times the change in Fahrenheit scale. So using this, I can find the conversion between Fahrenheit scale and Kelvin scale. So if you have a temperature in the Celsius scale, so we have Tf is equal to 9 over 5 Tc, but then I have to remember the 0 degrees Celsius corresponds to 32 degrees Fahrenheit. So using this relationship, I was able to convert from Celsius to Fahrenheit scale. And similarly, the conversion between Kelvin and Celsius will be the same for the Fahrenheit conversion. And for conversion from Celsius to Kelvin scale, if I add 273.15 Kelvin to a temperature reading in Celsius, I will get the temperature in the Celsius scale. So it's very easy to convert once you know this relationship for the readings on the calibration points of these three different scales. Now I want to give you an example. I have a temperature reading of 50 degrees Fahrenheit. So this is from the weather forecast for temperature, let's say in Istanbul. What is this temperature reading in the Celsius scale? What is this temperature reading in the Kelvin scale? Now, because I know that temperature in Fahrenheit scale is 9/5 Tc plus 32, I can use this relationship to get Tc is equal to 50 minus 32 times 5/9. So I realize that this is 18 times 5/9. That is 10 degrees Celsius. And how many Kelvin is 10 degrees Celsius? T is equal to Tc plus 273.15 Kelvin. So this will be 283.15 Kelvin. So tomorrow in Istanbul the temperature is 50 degrees Fahrenheit. It means the temperature will be 10 degrees Celsius or 283.15 Kelvin. So it's very easy to convert between different temperature scales using this relationship